let's spend one lecture here and review what's going to be for finals exam. Finals is going to be on Thursday, and it's going to be the same room that we had our midterm exam. So here are the material for exam. We're going to look at performance of AM in noise. And we have AM double-sideband large carrier, DSB suppressed carrier, DSB large carrier, and single-sideband. We kind of covered all of these guys. The second is performance of FM in noise. Which means, you know, stuff we covered, the processing gain, the thresholding effect, even pre-emphasis, de-emphasis, all of this. The third is what I call link budget calculation for AM and FM. And what are the link budget calculations? Remember, there are all sorts, those class of problems when I ask, well, this is the signal to noise ratio of the output, what is the input, how much do I need to transmit to close the budget, and the system performs adequately. A lot of problems are of this nature, right? Then signal and vector spaces. This whole notion of what does that mean, how do we define dot product, what do we mean when we say the signals are orthogonal, what is the norm of the signal, all of these questions. One-dimensional and two-dimensional signaling. Matched filter. And the last one is probability of error in binary pulse amplitude modulation. Right, the thing that we covered in the previous lecture. The exam is going to be 2 hours and 30 minutes, and it's going to be closed. What did we have last time? Closed book, closed notes with formula sheet. Okay. Expect 6 problems, or something like that, and you know, it's always going to be more than 100 grabs, but the 90 plus is going to be 8. Right? And I expect that you will get 9.
At the same time as the class time?
This is the same time as the class time. It's going to be 1, 2, 3:30 on Thursday.
Okay, so it's going to be like 3 hours?
It's 2:30.
It's enough for 6 problems?
Yeah. Yeah, I solved it in less than an hour today. So it's really, there's really no much math, so to speak, but I exercise kind of pretty much all of this theory with some simple examples.
What kind of table do we need to bring?
Bring whatever will make you feel comfortable. There is calculation with the Q function in the test. I'm going to put this table on the test. So Q table is going to be on the actual test. Other than that, I mean, your standard stuff, if you're shaky with Fourier transform, bring that table. Fourier series, bring that table. Whatever you think you might need, bring it, by all means. But as I said, there is not much math, right? So don't, but understanding is emphasized there. Any other questions? Go ahead.
Where is Q at on the series? Is that?
Where is Q table? Any other? So I have prepared some problems here. So let me go through some of them. I'll try to post all of this today so that you have today's lecture and problems. We'll see how much we go through. I hope I go through all of them, but if not, we'll have them solved. So unless there are any other questions, let me work out some example problems. So consider functions. Phi 1 of t is e to the minus t, and phi 2 of t is 1 minus a e to the minus 3 magnitude of absolute value of t. It says an interval is minus infinity to plus infinity. So it says determine A so that phi 1 of t and phi 2 of t are orthogonal. This is, I ripped this problem from previous comprehensive exams. So this one was on a comprehensive exam. So the question is, what is the value of A to make these two functions orthogonal? Now, when are the two functions orthogonal? Phi 1 of t is orthogonal to phi 2 of t if what happens to their dot product? Equal to 0. So this needs to be equal to 0. In our case, the interval is t goes from minus infinity to plus infinity. That's our interval here. And then phi 1 of t is e to the minus absolute value of t times phi 2 of t is 1 minus a e to the minus 3 absolute value of t. And then I need to integrate this over this interval. Now, this both of these functions are even functions. You can see that this one is even and this one is even too. Therefore, I can take this interval and replace it with twice interval from 0 to plus infinity. And then I can get rid of this absolute t. So this becomes e to the minus t, 1 minus a e to the minus 3t dt. Now these two integrals, this integral splits in two. So I have that the product of phi 1 of t and phi 2 of t is 2 times integral from 0 to plus infinity. The first one is just e to the minus t dt. And the second one is plus, or go ahead, minus a integral from 0 to plus infinity. And then I have e to the minus t, e to the minus 3t, which is e to the minus 4t. And then I'm going to say right away, d4t divided by 4. So to get that simplified. Now, what is the value of the first integral?
1.
1. What's the value of the second? 4. What's the value of the second integral? E to the minus 4t d4t. If I, instead of 4t, put x, that's e to the minus x dx. integral from 0 to plus infinity. That's the same as this. All right, 1. You follow what I'm saying? Why are you so puzzled? This whole thing here, if I take 4t into x, then this integral becomes integral e to the minus x dx, right? Where x goes from when t is equal to 0, x is equal to 0. When t is plus infinity, this is plus infinity. And this is 1, right? This is 1 factorial, or 0 factorial, so 0 factorial 1. So, and this needs to be equal to 0, so what is a? A is equal to 4. So if I set a equal to 4, these two functions become orthogonal. Right? It's as simple as that. Let's look at the next problem here. It says, consider a filter with a response given by this. Consider a filter with amplitude response h of f magnitude is equal to 1 over square root of 1 plus f over f0 to the power of n, where f0 is equal to 4 kilograms. This is a famous filter. This is a Butterworth filter, right? So just consider these kind of filters. N is the order of the filter. And I don't know if you have seen in the past, but sometimes we call Butterworth filter of the first order, or the second order, third order, and so on. This refers to this N. It says here the filter is presented with, that's part A, the filter is presented with white noise. Having a double-sided power spectral density n0 over 2 equal to 2 times 10 to the minus 4 milliwatts per hertz. Just a note of convention so that you don't get confused during the exam. If I write just n0, know that this is one side, right? If I write n0 over 2, know that it's double-sided, right? In case I forget to put that in a problem, right? So it's safe to, I try to be consistent. If I just write n0, then you know it's one-sided power spectral density. If I write n0 over 2, then you know it's double-sided. Determine the output noise power. Determine output noise power for n equal to 2. Part B, let me just give you all parts and then we'll go through each one of them. The filter is presented with a signal. S of t is equal to 2 cosine 2 pi f0 over 2t. So it is at 2 kilohertz. It's half of this frequency here. And it says determine the power, determine output signal to noise ratio. Output signal to noise ratio. How do we solve part A? We know this is the famous relationship that we derived in this course, and it's going to follow you, through the rest of your life. Right? If you have a random signal x that has a power spectral density Sx of f, and you have a linear filter that has a magnitude response of magnitude of h of f, then the power spectral density, the output, is equal to magnitude squared times the power spectral density and input. here, and then also power of output is going to be integral when f goes from minus infinity to plus infinity sy of f df, right? Or integral when f goes from minus infinity to plus infinity h of f magnitude squared sx of f df. That's these are fundamental relationships for this course. They will appear tomorrow on a test, right? Be sure, right? You cannot do anything that we did in this course without understanding how to calculate the leads. Now, in this case here, power of the noise, it's going to be, let me just say, power of the noise. And let me call it n, is going to be integral when f goes from minus infinity to plus infinity, h of f squared. So it's going to be 1 over 1 plus f over f0. Now we are asked to calculate only for n equal 2. So it's going to be this, times the power spectral density of the input, which is n0 over 2, times df. Right, so that's our power of the noise. This is an even function, so we can integrate only over one side. And I'm going to transform this as 2 times integral when f goes from 0 to plus infinity, and 0 over 2 comes outside. Then I'm going to write this df over f0 divided by 1 plus f over f0 squared. And then I'm going to put f0 to balance everything at the very end. Now, 2 and 2 cancels, and 0 and f0 go out. And what is the value of this integral? What is this is arctangent, right? So this is arctangent of f over f0 when f goes from 0 to plus infinity. What is the arctangent of plus infinity? Pi over 2x. So this is n0, f0, n0 over 2 times f0 times pi. So if you plug in the numerical values, this becomes n0 over 2 is 2 times 10 to the minus 4, 2 times 10 to the minus 4 milliwatts per hertz. F0 is 4 times 10 to the 3 hertz, and times pi. And this ends up being, or this is what I got, 0.8 pi in milliwatts. So that's the power of the noise. To determine the signal to noise ratio, I need to determine the power of the signal. Here's another relationship that you have to know, and be sure it's going to be on the exam. Don't even think you can wiggle out without knowing this one. What is the relationship? It's this guy. If you have a linear system here, which we represent in the frequency domain with the frequency response h of f, and I have a sinusoidal at input s of t, let me call this y of t, and s of t is going to be a cosine 2 pi f0 t, f0 t. Then y of t is going to be a times the magnitude response, which is going to be magnitude of f equal to f0, and then times cosine 2 pi f0 t plus the angle of h of f equal to f0. This is the formula that you derived a long time ago in circuit theory, I think, that tells you what happens when you present the sinusoidal to the linear system. What happens is you get the sinusoidal of the same frequency that will be changed in the magnitude and in the phase. The magnitude is going to be multiplied, whatever is the magnitude of the input times the magnitude response of the filter, and then the phase is going to be whatever is the phase in the input adding the phase Now, if I were to look at the power of the output, since this is a pure sinusoidal, it is just going to be A times H of F equal to F0 squared divided by 2. This guy plays no role because the power of the sinusoidal does not depend on its phase. It just depends on its magnitude. Right? So if I were to calculate the power of the output, I would take the magnitude of the output squared divided by 2. So to calculate signal-to-noise ratio in this problem, I already calculated the power of the noise. What I need to do is calculate the power of the signal. Well, to evaluate the power of the signal, I need to calculate what is the signal, the amplitude response of the filter and the frequency of the signal. So in our case, H, so let me put the qualifier here. In this case, I have H of F equal to F0 over 2, because that's my, if you look at that's the power of, or that's the frequency of my sinusoidal. So in this case, this becomes 1 over, well, I need the square of that, so let me just do the square. It's going to be 1 plus F0 over 2 divided by F0 squared. Right? That's the magnitude squared. And this becomes 1 over 1 plus 1 over 2 squared, which when everything is said and done is 4 over 5. Okay? So now, the power of the output signal and the output is going to be the magnitude and the input squared. So what did I put as a magnitude? Magnitude is 2. All right? So the magnitude of the input squared, which is going to be 2 squared times 4 over 5 divided by 2. And this is 4 times 4 is 16 divided by 2, 8. So it's 8 over 5. I did everything correctly. Therefore, signal to noise in the output is going to be C power of the signal, which is 8 over 5. And then power of the noise, which is 0.8 times pi. But this is in watts, right? So it's 0.8 times pi times 10 to the minus 3, right? In watts. And I don't have this calculated correctly, but let me just do it here. I think I have, but I might be wrong. No. So this is 8 divided by 5 divided by 0.8 times 5. So this is 636 times 0.6, which it is customary to express this in dV, but this is 20 dV.
It's 8 over 5 watts, is that right? 8 over the same power?
Yeah, because this is in, when I say like this is in volts. So it's just, there's no mirror. But out of all of this stuff that is in this problem, really, this is what, I'm testing, right? This is absolutely, required for an electrical engineer to understand. Any questions here? Okay, let's look at the next problem. It says, consider a system using double-sideband large carrier. This is one of those linked budget problems. It's using double-sideband large carrier modulation scheme. the following information are known. Bandwidth, which is 2 times W, is 40 kilohertz. Signal to noise ratio at the output is 35 dB. That's the required signal to noise ratio. This is dictated by the performance of our information signal. The modulation index, A is equal to 0.4. Power of the message normalized is 1/2. And the power spectral density of noise is 4 times 10 to the minus 17 milliwatts per hertz. This is one-sided. Right? That's why I gave it as N0. It says determine required signal to noise ratio of the input. So determine signal to noise ratio and input. Since this is a double-sideband large carrier, we know the relationship. In all of these analog modulation schemes that we covered, input and output were related to processing gain. Now, signal to noise ratio at the output, in a case of a double-sideband modulated large carrier, was equal to 2A squared, power of the message normalized, divided by 1 plus A squared, power of the message normalized, times signal to noise ratio and the input. Now this is in a linear domain, so you would have to look at this in the dB. From here, signal to noise ratio in input expressed in dB is going to be whatever is the signal to noise ratio at the output expressed in dB minus 10 log of 2A squared, power of the message normalized, 1 plus A squared, power of the message normalized. Right, so that's our relationship between input and output signal to noise ratio. So now, if you substitute, so you get signal to noise ratio and the input needs to be 35 dB, which is the required signal to noise ratio at the output, minus 10 log of 2 times 0.4 squared times 1/2 over 1 plus 0.4 squared times 1/2. And this gives us 43.3 dB. Remember, in all the modulation schemes, our processing gain was positive, meaning that as the signal goes to the receiver, it actually increases the signal to noise ratio. The only difference was double-sideband large carrier. And the reason for that is not that the receiver is not performing. The reason is because in a signal to noise ratio calculations at the input, the carrier power is taken as a part of the signal. In the output, only the message signal power is taken as a part of the signal. Since majority of the power in the double-sideband large carrier is in the carrier, it appears that the processing gain here is smaller than 0. So therefore, when you do these calculations, it will be always smaller than 0. Go ahead.
If the power of the message signal is not provided, are we also going to assume that it's 1/2?
Assume it's 1/2. That's your, if you're modulating with just a tone, right? And a lot of these analog systems are tested by assuming pure sinusoidal. Right?
I mean, if a message signal is given to us, there's a way to actually calculate the power of the message signal.
Then you're absolutely right. You know, that means if I give you signal, I give you its power as well. Right?
And so it might not always be 1/2.
No, you're right. It might not be 1/2. If I give you a message signal, then you're expected to calculate this power. Okay. Good question. So the part B, it says determine receiver sensitivity. What is the receiver sensitivity? It's a minimum power of the signal at the input receiver that meets the signal-to-noise requirement for the whole system. If I know what the signal-to-noise ratio at the input is, and I'm able to calculate what the noise power at the input is, then I can easily calculate what the signal power is. So the signal power at the input is going to be noise at the input expressed in dBm plus the signal-to-noise ratio at the input. Noise in the input, it is actually the noise after pre-detection filter, after the front-end filter. So in this case, since I know the bandwidth, I'm assuming that my front-end filter is the same as the bandwidth of the signal. So the noise at the input is going to be N0 times the bandwidth. Actually, I'm going to write this as 10 log of N0 times the bandwidth, and then plus signal-to-noise ratio at the input expressed in B. In this case, this becomes 10 log of 2 times the bandwidth of the signal. Well, it's 40 kilohertz, right? So 0. So it's 40 times 10 to the 3 hertz times the power spectral density is 4 times 10 to the minus 17 milliwatts per hertz. And when you calculate this, this is minus 117.95 dBm. So that's the power of the noise. Plus, I guess here I should put 43 dB. So plus 43.3 dB. And this gives me a power of the signal, which needs to be minus 74.66 dBm. So that's the power of the signal that I need to deliver to this receiver. If I deliver this much power to the front end, then the signal-to-noise ratio at the front end is going to be 43 dB, and after demodulating, the output signal-to-noise ratio is going to be 35 dB. So I'm going to meet the performance. If I go above this, then my signal-to-noise ratio is better than 43, and therefore the signal-to-noise ratio in the output is going to be better than 43. And so this is like a minimum performance requirement. And then the last, if the path loss between transmitter and receiver is 100 dB, what should be your transmit power? Determine transmit power. Well, the transmit power, PTX, is going to be your S in dBm plus the path loss in dB, which in our case here is minus 74.66 dBm plus 100 dB, and this gives me 25.34 dBm. I usually convert that into watts at the end to get a better understanding. So it's around a little bit shy of the half a watt that I need to transmit so that I can overcome 100 dB of the power. Go ahead. Any questions? No? Okay. All right, so that's a link budget problem using double-sideband large carrier. Let's look at the similar problem with FM. It says, consider a system, analog system using FM modulation. The following parameters are known. The transmit power is 100 watts. the W, which is the baseband bandwidth of the message signal, is 15 kilohertz. Path loss maximum is 120 dB. That's the maximum path loss that I need to overcome in my system. Signal to noise ratio, the output, is 40 dB. And then single-sided power spectral density is 2 times 10 to the minus 14 milliwatts per hertz. Sorry, double-sided, right? Segregated. And then power of the message normalized is 0.5. So I'm still working with a single tone. Determine minimum signal power at the receiver. Okay, so part A, determine minimum signal power of the receiver. Now, usually we worked in all the problems I did so far, we worked from the receiver to the transmitter. Now I'm working on the downside. So we have the transmitter power, and I'm trying to estimate how far did we get. So if I have, this is my transmit power and this is the loss, I can determine easily what is the highest power, minimum power at the receiver. It's going to be my transmit power in dBm minus the path loss in dB. And in this case, this is 100 watts, that's 50 dBm, minus 120 dB. So this gives me a power of minus 70 dB. So that's the power that my signal will have at the receiver at the furthest distance, or the furthest path loss point. The question B, it says, determine beta. Okay, so we need to figure out how do I determine beta. There are two things that I know here. The first one is that signal signal out, signal to noise ratio at the output is going to be signal to noise ratio at the input plus the processing gain expressed in dB. So that's my first relationship. The second one is that signal to noise ratio at the input is going to be whatever is the noise in dBm plus the signal to noise, actually, whatever is the signal in dBm minus whatever is the noise in dBm. So that's my second relationship. So I have two relationships here that help me with this balancing act in FM. In FM, you improve your performance with data in terms of processing gain improves, but your also bandwidth grows, so you're limited by the increase in bandwidth. So now if I look at the first relationship, I can express the signal to noise at the input in dB just make sure that I switched relative to my notes, right? So let me just follow what I have on the board. So signal to noise ratio at the output in dB is going to be whatever is the signal to noise ratio at the input expressed in dB, and then plus processing gain. The processing gain is 10 log beta squared 1 plus beta. There's 3 here. times 2 times power of the message normalized. So that's the first equation that I have. From the second equation here, I'm looking at after this guy. So signal to noise ratio at the input is going to be whatever is the signal in dBm minus 10 log. What is the bandwidth? It's N0 times the bandwidth, and the bandwidth is 2 times 1 plus beta times. And so that's the power of the noise at the input. Now, if you combine, let's see what are the things that we know. We know this guy, right? And we know this one. So I can take this and put it in here instead of this signal to noise ratio input, right? So you get signal to noise ratio, and the output is going to be S signal in dBm minus 10 log and 0 times 2 times 1 plus beta times W, and then plus 10 log of 3 beta squared 1 plus beta times 2 power of the message normalized. Now, I know everything here except beta, right? I know what the output needs to be, and I know what my input signal power is. I know N0, I know W, so the only thing that I don't know is beta. If you substitute, you get 35 dB is equal minus 70 dBm minus 10 log of this. So it's 2 times 1 plus beta times N0 and times W. So N0 is 2 times 10 to the minus 14 and times 15 times 15 times 10 to the 3. So that's the upstairs here. And then this thing here is going to be 3 times beta squared times 1 plus beta and times 2 times 1. So you can see that this and this cancels, and after some shuffling here, we get here 35 is equal to minus 70, and then I have minus 10 log, and let's see what I have here. 2 times 10 to the minus 14, 15, 10 to the minus 3, and this 3. If I did everything this correctly, this end up being 2 times 10 to the minus 10. Okay? And then I have plus 20 log of beta, where everything is rearranged. And then from here you can see that this is equation only in beta. So you end up with 8 is equal to 20 log of beta, and beta is equal to 10, 8 over 20, which ends up being 2.51. So what is the point of this problem is knowing that these two equations work simultaneously, right? That your output is input signal to noise ratio plus the processing gain, but also as your bandwidth, as your beta increases, even though your processing gain increases, your signal to noise ratio input will decrease, right? Because the noise rises linearly as beta while the signal power stays the same. And then kind of just the rest of it is just simple algebra. Okay, let me do at least let me do a couple more. This is problem number 5. it says, consider a signal given in figure. So I have a signal that looks like this. This is from 0 to t. Here it is. S of t. It says I'm going to use this signal for signaling, and it says sketch the matched filter impulse response for this signal. So sketch the impulse response of the matched filter Now you remember that matched filter h of t has an impulse response s of t minus t. So you have to take this signal, flip it over, and delay it by t. So how would that look like? This is t. It exists from 0 to t, but it looks like this. Right? So this is h of t. That's the matched filter response. Part B, if this is, and I have this here, it's A. It says if A is equal to 0.1 and 0 is equal to 2 times 10 to the minus 3 baud per hertz, it says determine the signal to noise ratio in the output of the matched filter. Now what we know is that signal to noise ratio in the output is going to be equal to 2 epsilon s over 0. This is always the case, right? Whenever I'm receiving with a matched filter, my signal to noise ratio of the output is equal to this. Now in this case, and in any other case, epsilon s is equal to signal squared over t dt, where we integrate between 0 and t. This is the power of the modulated signal. In this particular example, this is integral from 0 to t. The s of t can be expressed as a times t over capital T, and I have to square that t. And then if you do the integration, this is a squared over t squared t third over 3, 0 to capital T. So epsilon s is going to be a squared times t over 3. And therefore, our oh, I forget, that's what I'm missing here. T is equal to 1. So that's part 1. So your signal to noise ratio in the output becomes 2 times epsilon s, 2 times a squared t over 3 divided by n0. In our case here, this becomes 2 times 0.1 squared times t, which is 1 divided by 3, and divided by 0, which is 2 times 10 to the minus 3, which is 3.33, 5.2. Okay. So what you need to remember always this relationship here. The output of the matched filter is always 2 times epsilon s over n0.
So that's the question. How did you determine the function for s squared of t? I know you put
This
at over t, but how did you get that?
Well, that is kind of always problematic, right, thing from where you guys stand. This is a straight line, right?
It's slope,
So S of t in general is a t plus b. Okay, it's a straight line. This is the equation of a straight line. Now, every straight line that goes through origin, what is b in that case? 0, right? So this guy has equation at. And now it's a matter of saying, well, when t is equal to capital T, what is the output? Has to be a. So then I just kind of look at, okay, this needs to be a when t is equal to capital T. So if I make t equal to capital T, I want them to cancel, and then this is a. Or you can say this as a, what is the slope of this line? It goes a units for every t unit on downstairs. So the slope is a over t. Now, how do you get that? I mean, a lot of times you just have to be a little skillful, right? And you already ran into these problems when you were doing Fourier series and stuff like that. Because it always had, you know, if I give you stuff graphically, you had to come up with some sort of analytical expression so that you can repeat.
In your old review, I got this one. Can you teach us how to make it?
Yeah, sure. Which let's see. Okay. Oh yeah. Here it's a very similar problem, I guess. It's just that S of t is slightly different.
Yes, we would like to know S of t.
Just how you sketch the
how
to
to
match
determine
filter,
the
right?
S of t.
Age of t, right?
S of t.
He's curious about adding on the slope of 0 there, whenever you determine the S of t and the epsilon of s. Is that right?
You mean the let's do this problem. It's the
Okay.
same problem, just a slightly different S of t. So here, S of t is slightly different pulse that I'm using for signaling. But let me finish, before I go there, let me finish this problem, right? It says, I'll come back to this, right? It says, if this signal is used for BPSK signaling, what is the probability of error, right? And so part C, BPSK, BPSK signaling. What is the probability of error? We derive today probability of error in a BPSK is given a square root of Q over square root of 2 epsilon s over n0. Right? That's the expression that we derive today. So if you so this is going to be Q or square root of 3.33, which is Q of 182. And then if you go to a Q table, this gives you 3.6 times 10 to the minus 2. So probability of error is slightly under 40%. Okay. So just this Q table will just be columns where you get the value of whatever is underneath here, and then the Q of that graph. And Q function falls rapidly, so after 4 or 5, the value is so small that it's rarely topic. So here the question was, this is the all notes review, and this is problem number 5. And it's essentially the same problem. It's just that your S of t is given like this. This is t over 2. This is t, S of t, and this is a. And the question is, first, sketch the impulse response of the matched filter. So what is age of t? The way how you approach this is 2 steps. 1, sketch S of minus t. That's the first step. Take this signal and sketch minus of its version. So how does the minus look like? Grab the signal and flip it over. Right? So S of minus t looks like this. This is minus t over 2, minus capital T. It looks like this. So this is S of minus t. Now my meshed filter is H of t is equal to S of capital T minus t, which better way to write this would be S of minus t minus capital T. You see that this is the case? It is minus t minus capital T. So take this signal and delay it t in a time domain, right? Because now instead of, this is S of minus t, so instead of t, put t minus capital T. So you delay it this way, right? So you take this and you move it t to the right. So you end up with the signal where H of t, so this is t, and this is how this guy looks like. So this is H of t. Okay. Now, the question is, what is the energy of this signal? Right? How would you calculate the energy? Well, energy of the signal is always integral from 0 to t, s squared of t dt. Now, in this case, we cannot really come up with a unique expression. You have to have two expressions, right? So this becomes an integral from 0 to t over to, I guess, just a dt, but I have to square it. And then plus an integral from t over 2 to t. And now it's the tricky part. Now it's this one here. So how do I look at this one? Well, what is the slope? It goes a units down by t over half increment along the x-axis. So the slope has to be minus a over t over 2, right? Times t. And then when t is equal to 0, where does this function hit here? When t is equal to 0, extend this straight line. Where is it going to intersect here? 0. That when t is equal to 0, what is y? 2a. 2a. So it's plus 2a, and then squared dt. That's a straight line, right? Now you want me to go through this again? Yeah. So look at this straight line. What is the slope? It goes a units down for t over 2 increment, right? So it goes that many volts per that many seconds, right? So it goes 8, it decreases, falls down by minus a over the time of t over 2, right? So that's a slope. But all the functions, all of these lines have the same slope, right? So which one of these lines I'm talking about? Well, I can do this two ways. I can say when t is equal to 0, this will be at 2a, right? So I put t equals 0 here, and then this needs to be equal to 2a. Or I can do it alternatively. I can say when t is equal to capital T, that this better be 0. Y is equal to 0. So if I make t equal to capital T here, you can see t and t cancels, 2a minus 2a, then I have to get 2a to cancel. So either way, you can either anchor this point here or anchor that point here, but
We can't take also 2 points and find
yeah, there's many different ways, right? Okay. So now that I have this is quite easy. So this is a squared times t, so it's t over 2, and then plus. Now this is what I also quite often do. Instead of integrating now this squaring and all of that stuff, you make this d, you multiply here by 2a over t, and divide by 2a over t. I can write this d, let me just do it this way, d of 2a over t times t plus 2a times t over 2a. Minus. Minus here. So what did I do? I'm making this the same as this, right? And you can see that here 2a over t cancels with this, so this whole thing here is dt. But I'm making it so that I can integrate this in one shot. Right? So this becomes plus, this is x squared dx, right? So I'm going to put here minus t over 2a. And then I have minus 2a t over capital T plus 2a cubed over 3. T goes t over 2 capital. And if I didn't make any mistakes, let's just evaluate this. So it's a squared times t over 2 minus t over 2a. When I substitute capital T here, what does it become? T over T is 1, minus 2a plus 2a is 0. So the first one is 0. Minus, when I substitute T over 2, then T over 2, I get minus a plus 2a is 8. So minus a cubed over 3. And then it's easy now to add this, it's a squared t over 2 plus a squared t over 6, right? A squared t over 6. So this is 3 plus 1 is 4 divided by 6 is 2. So it's 2 a squared t over 3. Now, watch, but this is not correct. It is problem, right? Oh, it's not, right?
Excuse me. This kind of problem is going to be the final. It's losing time sometimes. Or it's going to be.
Well, I may be doing it complicated from where you stand, but this integral is easy, right?
You added 2a there, but
Yeah, you can square it and
But-
but you didn't subtract 2a when you added in
where?
and the dt. You add 2a t over t plus 2a.
Plus
Yeah.
2a, okay?
And, why you didn't subtract?
Well, if I take dt plus anything, let's say gamma, is what? That's the same as dt. So I can always add here whatever I want, as long as it's a constant. Right. But I still make somewhere, there's
I
a,
have a question for you, sir. You ended up calculating the slope, and it seems to me that when you went from 0 to t over 2, that the slope of that is going to be 0. So I would think that function of t would actually be a function of 0.
no function of 0, it's a constant, right? It's
The
constant.
slope is 0.
But what's the constant of this, if I, yeah, so this here, a, I can understand as 0 times t plus 8. So what is the slope? 0. What's the intercept? 8. You're right.
Square.
So where did I make somewhere? Which one is?
E squared to s squared. To s squared for
This one?
yeah.
2a. 2A,
Do something.
Should it be for a square or not?
Where?
When you get to A out of the,
Here?
understand?
No.
Here?
Yeah, there, then plus to A,
Plus A, okay, square.
yeah.
D of this times that. Everything is fine, so this goes outside, then this cube over 3.
Maybe the mistake in the note.
Yeah,
Yeah.
that's
Yeah.
also possible, right? So I'm thinking there's a mistake in the note. Why am I thinking that? Because, look, the energy of, yeah, there's probably a mistake in the
Yeah.
note. This is, the energy is the energy of this one plus the energy of this one. The energy of this one is A squared times T over 2, so it has to be greater than that, right? So here I'm saying, okay, it's greater than half, so it has to be 2/3. So this is probably correct, the notes are not.
We're getting another one, another problem?
I have a doctor's appointment at 4.
Ah,
I need to really run.
Sorry.
So, that's kind of, you can see these problems are not very hard. And I just did the exam, so I know, usually I make it the last minute, but I made it last night. There's not much math. So if you're doing like, pages of math, stop. And then think about what is it that you're doing. Because a lot of these are just one-liners, right? How you calculate. But you have to understand what the question means and what the answer is supposed to be.